this video, we'll explore our extensive family tree of isomers, revisiting familiar types and investigating a subcategory of stereoisomers, optical isomers, in greater detail. We'll introduce the concept of chirality, explain what distinguishes chiral from achiral molecules, and discuss enantiomers and diastereomers. We'll also cover how to assign RNS absolute configurations to asymmetric centers using CIP priority rules, and how to identify Meso compounds. Up until now, we've explored various types of isomers. Let's revisit the concepts, starting with the definition of isomers. Isomers are different molecules that share the same molecular formula. If two molecules have different molecular formulas, they are not considered isomers. Isomers with different atom-to-atom connectivity are called constitutional isomers, while those with the same connectivity but different spatial arrangements are known as stereoisomers. Stereoisomers can be further divided into subcategories. Stereoisomers that can be interconverted by rotation around single bonds are known as conformational isomers, while those that cannot be interconverted by bond rotation are referred to as configurational isomers. Finally, within configurational isomers, molecules that exhibit isomerism due to restricted rotation around a double bond or within a rigid ring structure are referred to as cis-trans or geometric isomers. These are the types of isomers we've encountered so far. Here's a helpful flowchart that illustrates how these isomers are related, resembling a family tree. There are also subcategories of constitutional isomers, but we won't focus on them much in this course. There is one final group of isomers we'll explore in this course, a subcategory of configurational isomers known as optical isomers. These isomers have unique properties and are further divided into two categories, enantiomers and diastereomers. Optical isomers are stereoisomers that are chiral. Chirality is a property of asymmetry where an object or molecule cannot be superimposed on its mirror image, meaning the two mirror images cannot perfectly overlap. Conversely, objects or molecules that are achiral are superimposable on their mirror image, meaning they have a plane or point of symmetry that makes them indistinguishable from their mirror image. Let's start by observing examples of chiral and achiral objects before moving on to molecules. Our hands are a perfect example to explain chirality. In fact, the word chiral actually comes from the Greek word chair, meaning hand. The palms of our left and right hands are non-superimposable mirror images. No matter how much we try, we cannot align or superimpose the front faces of both hands perfectly. Meanwhile, this flask can be superimposed on its mirror image due to its internal plane of symmetry, making it achiral. Let's move on to what makes a molecule chiral. A molecule is considered chiral if it lacks an internal plane of symmetry, meaning it cannot be superimposed on its mirror image. This typically occurs when a tetrahedral carbon atom is bonded to 4 different groups, creating an asymmetric atom, also known as a chiral center. Asymmetric carbon atoms are often regarded as stereogenic elements because they can lead to pairs of stereoisomers. Because of this, the number of stereoisomers for a molecule with n stereogenic elements is typically calculated using the formula 2 to the n power. A molecule is considered achiral if it has an internal plane or point of symmetry. For example, these 3 molecules are all achiral because they contain one or both of these elements of symmetry. In this substituted cyclodiene, the molecule is achiral due to 2 internal planes of symmetry. In contrast, the staggered conformation of this stereoisomer of 2,3-dibromobutane lacks a plane of symmetry, but is achiral because it has a center of inversion at the midpoint between the 2 central carbon atoms. This point of symmetry means that for every atom or group on one side, there is an equivalent atom or group directly across the center of inversion, making the molecule superimposable on its mirror image. Finally, trans 1,2-dichloroethylene is achiral due to the presence of a plane of symmetry and a center of inversion between carbons 1 and 2. Let's move on to drawing enantiomers and distinguishing between two stereogenic elements. Here we have a generic carbon center attached to four different groups, labeled 1 through 4. Initially, these two molecules are identical because they have an internal plane of symmetry and can be superimposed on each other. To make these molecules enantiomers, we can swap the positions of any two groups attached to the carbon center. Notice that this simple change disrupts the internal plane of symmetry, making these mirror images no longer superimposable. Swapping the positions of any two substituents again returns the molecule to the original conformation, making these molecules once again superimposable. Therefore, there are only two ways to arrange four different substituents around a tetrahedral carbon, which is why a molecule with one asymmetric center exists as a pair of stereoisomers. We can also draw enantiomers by creating a molecule's mirror image. Here is the same molecule again, now drawn as a pair with its mirror image. Although the positions of the substituents appear identical, rotating the molecule reveals that they are indeed enantiomers, just as we observed before. Let's observe this in molecules we've already seen. In lactic acid, the central carbon is attached to a hydroxyl group, a carboxyl group, a methyl group, and a hydrogen atom, creating an asymmetric or chiral carbon. Lactic acid therefore has one stereogenic element, meaning it can exist as a pair of stereoisomers known as enantiomers of lactic acid. Here's one more example. In the amino acid valine, the central carbon is attached to an amine group, a carboxyl group, an isopropyl group, and a hydrogen atom, resulting in an asymmetric or chiral carbon. Valine therefore also has one stereogenic element, meaning it can exist as a pair of stereoisomers known as enantiomers of valine. Now we know how to differentiate between two enantiomers of a molecule with one asymmetric carbon center. However, here we encounter a new problem. For example, consider the following molecule. In this molecule, the central carbon is attached to a hydroxyl group, an amino group, a methyl group, and a hydrogen atom, making it a chiral carbon. As a result, the molecule has one stereogenic element and can exist as a pair of enantiomers. Here's the problem. If you need the specific enantiomer shown on the left for a reaction, simply naming the molecule 1-amino ethanol using IUPAC nomenclature doesn't indicate which enantiomer you're referring to. The Kahn-Ingold Prelog CIP system allows us to distinguish between chiral centers by assigning them absolute configurations, designated as R and S. Here is how we use the CIP priority rules. Prioritize the four groups around a chiral center based on atomic number, assigning the highest atomic number as priority 1 and the lowest as priority 4. Now orient the chiral center so that the lowest priority substituent is pointing away from the viewer, or positioning it on a dashed bond. Draw a curved arrow tracing the path that intersects priorities 1, 2, and 3 in order. If the path is clockwise, the chiral center has the absolute configuration R, from the Latin word rectus, and if the path is counterclockwise, the chiral center has the absolute configuration S, from the Latin word sinister. Applying these rules, we find that the specific enantiomer of 1-amino ethanol we want has the R configuration. Therefore, we would refer to this molecule as R1-amino ethanol, while its enantiomer would be called S1-amino ethanol. In this example, we assigned the name for the S enantiomer of 1-amino ethanol by recognizing that it was an enantiomer of the structure we labeled as the R enantiomer. Suppose we didn't name the R enantiomer first, and we wanted to determine the absolute configuration of the S enantiomer. The standard way to do this would be to rotate the molecule such that the lowest priority group, or the hydrogen, is on a dashed bond. From there, we can see that this molecule has the absolute configuration S. Alternatively, we see that the lowest priority group, hydrogen in this case, is positioned on the wedged bond. We can trace a path covering priorities 1, 2, and 3, which would give us a path in the clockwise direction, corresponding to the absolute configuration R. However, because we started with the hydrogen on the wedge instead of the dash, we would flip the absolute configuration of this chiral center from R to S. Consider one final scenario. Suppose the lowest priority group was on a bond in the plane of the page rather than on a wedged or a dashed bond. Once again, the standard method would have us rotate the molecule such that the lowest priority group is on a dashed bond, from which we can trace a path and determine the absolute configurations as we've been doing. Alternatively, we can take advantage of the fact that swapping any two substituents on a molecule with one asymmetric carbon gives us its enantiomer, and swapping any two substituents again returns the molecule back to its original configuration. In this example of 1-amino ethanol, the lowest priority group is positioned in a bond in the plane of the page. By swapping its position with the substituent on the dashed bond, we have flipped the chiral center's absolute configuration. From here, we can label the groups based on their priorities, and tracing a path appears to be in the clockwise direction, corresponding with the R configuration. However, because we swapped the positions of the amino group and hydrogen earlier, we need to swap back to their original positions. This second swap returns the chiral center to its true configuration, which is S. In our example so far, each of the substituents has had different atomic numbers, making it easy to assign priorities. Let's take a look at a less straightforward case. In the hemiacetal 1-methoxyethanol, two oxygen atoms are directly bonded to the asymmetric carbon center. In the previous example, all substituents had different atomic numbers, making it straightforward to assign priorities. But how do we assign priority between the hydroxyl group and the methoxy group? To determine priority, we look at the atoms directly bonded to the chiral center. If two atoms are the same, like the two oxygen atoms here, we then move to the next atoms they are bonded to. The hydroxyl group OH is bonded to a hydrogen, while the methoxy group OCH3 is bonded to a carbon, which takes precedence due to its higher atomic number. Therefore, the methoxy group gets the higher priority, and using the steps we learned earlier, we can determine the absolute configurations for these enantiomers. So far, we've focused on molecules with a single chiral center. Now let's examine structures with two or more stereogenic elements. The following structure is a stereoisomer of tartaric acid, which has two chiral centers at carbons 2 and 3, each bonded to 4 different groups. Using the CIP priority rules, we can determine the absolute configurations of these chiral centers. For carbon 2, the lowest priority group is already on the dashed bond. The hydroxyl group is priority 1, the carboxylic acid group is priority 2, and the remaining branch is priority 3. Tracing the direction of the priorities gives us a clockwise direction, assigning this chiral center the R configuration. Using the same process for carbon 3, we find that this carbon also has the R configuration as well. Therefore, we can give this molecule the name 2R, 3R, tartaric acid. Tartaric acid has 3 additional stereoisomers, which can be determined using the formula for the number of stereoisomers, 2 to the n power, where n is the number of stereogenic elements. Since tartaric acid has 2 chiral centers, n equals 2, resulting in 2 to the second power, or 4 total stereoisomers. Let's observe these remaining stereoisomers, starting with the enantiomer of 2R, 3R tartaric acid. To make the enantiomer of a molecule, we simply swap the positions of 2 substituents at all chiral centers. Swapping the positions of the hydroxyl groups on the wedges with the hydrogens on the dashes, we can make the enantiomer of 2R, 3R tartaric acid, 2S, 3S tartaric acid. These two molecules are non-superimposable mirror images, making them enantiomers. We can identify the remaining stereoisomers of tartaric acid by changing the configuration at one chiral center while keeping the other the same. Starting with the 2R, 3R stereoisomer, keeping the configuration of carbon 2 the same, and swapping the configuration of carbon 3 gives us 2R3S, tartaric acid. 2R3S tartaric acid is not a non-superimposable mirror image of either the 2R3R or 2S3S isomers because the configurations differ at one chiral center. Therefore, 2R3S tartaric acid is a diastereomer of 2R3R and 2S3S, meaning it is a stereoisomer that is not an enantiomer. Compounds with 2 or more stereogenic elements can have multiple diastereomers. In a pair of enantiomers, all chiral centers have opposite RS configurations. If even one chiral center does not have the opposite configuration in the mirror image, the result is a diastereomer, as the molecules are no longer non-superimposable mirror images. Let's move on to identify the last stereoisomer of tartaric acid. Like before, we can swap the configuration at both chiral centers to give us the final stereoisomer, 2s, 3r, tartaric acid. Just now, we learned that in a pair of enantiomers, all chiral centers have opposite RS configurations. So following this logic, wouldn't this make 2R3S and 2S3R tartaric acid enantiomers? Turns out 2S3R tartaric acid is not the enantiomer of 2R3S tartaric acid, even though they have opposite configurations at all of their chiral centers. Rotating around the C2-C3 bond, we see that both 2S3R and 2R3S tartaric acid have a mirror plane of symmetry within the molecule, making these molecules achiral, and as a result superimposable on each other, making them the same molecule. We call compounds like RS tartaric acid meso compounds, which are molecules with chiral centers that contain an internal mirror plane of symmetry, making them achiral. Therefore, there is a corollary to the rule that swapping the configuration at every chiral center of a molecule gives its enantiomer. This is only the case if the compound itself is chiral. Flipping all the chiral centers on a meso compound will result in another achiral compound. As always, let's do some practice. For each of the following molecules, A. Identify whether the molecule is chiral, achiral, or meso. B. Assign the RS configuration to all chiral centers. C. Determine the total number of possible stereoisomers. For the first 5 structures, draw all stereoisomers and describe their relationships, enantiomers, diastereomers, or meso compounds. Feel free to pause the video and try solving this problem on your own first. Methadone has one asymmetric carbon atom bonded to a nitrogen, a methyl group, a hydrogen, and the remainder of the molecule, making it chiral. In this stereoisomer, the chiral center has an R configuration. The nitrogen is the highest priority group, followed by the carbon attached to the rest of the molecule, then the methyl group, and finally hydrogen as the lowest priority on a dashed bond. Tracing the priorities in a clockwise direction confirms the R configuration. Since methadone is not a meso compound, it exists as a pair of enantiomers, R methadone and S methadone, with a total of 2 stereoisomers. Nicotine has one asymmetric carbon atom, which is bonded to a pyridine ring, a hydrogen atom, a nitrogen atom, and a carbon in the pyrrolidine ring, making it a chiral molecule. In this stereoisomer, the chiral center has an S configuration. The nitrogen is the highest priority group, followed by the carbon in the pyrrolidine ring, then the carbon in the pyridine ring, and finally hydrogen as the lowest priority. Tracing the priorities gives an R configuration, but because the lowest priority group, hydrogen, is on a wedge, the configuration is flipped to S. Nicotine exists as a pair of enantiomers, R nicotine and S nicotine, with a total of 2 stereoisomers. Phenobarbital has no asymmetric carbon atoms and an internal plane of symmetry, making it an achiral molecule. As a result, phenobarbital does not have any stereoisomers and exists in only one configuration. Trans 1,2-dimethylcyclohexane is often drawn in a chair conformation, which can make determining chirality and absolute configurations challenging. A useful approach is to flatten the ring into a 2D structure with wedged and dashed bonds. In this view, the molecule has 2 asymmetric carbon atoms at positions 1 and 2, each with chiral centers. For carbon 1, the highest priority group is the carbon bonded to the adjacent carbon with the methyl group, followed by the other ring carbon, then the methyl group, and finally hydrogen. Tracing the priorities gives a clockwise direction, R configuration, but since the hydrogen is on a wedge, we flip to S. For carbon 2, the highest priority group is again the adjacent carbon with the methyl group, followed by the other ring carbon, then the methyl group, and hydrogen. Tracing the priorities in a counterclockwise direction directly gives the S configuration since the hydrogen is already on a dash. This molecule, also called 1s2s 1,2-dimethylcyclohexane, has 2 stereogenic elements, so we can assume that it can exist as 4 stereoisomers, 1r2r, 1r2s, 1s2r, and 1s2s minus 1,2-dimethylcyclohexane. However, while the molecule appears to have two stereogenic centers, it is actually a meso compound due to its internal plane of symmetry. This symmetry causes the 1R, 2S, and 1S, 2R configurations to be identical, superimposable mirror images, making them the same molecule. As a result, the molecule only exists as two distinct stereoisomers, the meso form, which is achiral, and the pair of enantiomers, 1R, 2R, and 1S, 2S. Ephedrine has two asymmetric carbon atoms, making it a chiral molecule with two chiral centers. In this stereoisomer, carbon 1 has an R configuration and carbon 2 has an S configuration. For carbon 1, the highest priority group is the hydroxyl group, followed by the carbon in the ethylamine chain, then the phenyl group, and finally hydrogen. Tracing the priorities gives an R configuration. For carbon 2, the nitrogen in the ethylamine chain takes priority, followed by the carbon in the hydroxyl group chain, then the methyl group with hydrogen as the lowest priority. Tracing gives an S configuration. Ephedrine has two stereogenic elements, and because it isn't a meso compound, it can exist as four stereoisomers: 1R, 2S, ephedrine, 1S, 2R, ephedrine, 1R, 2R, ephedrine, and 1S, 2S, ephedrine. D-ribose has three asymmetric carbon atoms, making it a chiral molecule with three chiral centers. In this stereoisomer, all three asymmetric carbons have the R configuration. For carbon 2, the highest priority group is the hydroxyl group, followed by the carbon bearing the aldehyde, then carbon 3 with the hydroxyl group, and finally the hydrogen. Tracing the priorities gives an R configuration. For carbon 3, the highest priority is the hydroxyl group directly bonded to it. The second highest priority group is the branch containing carbon 2, as the aldehyde at the end of this branch takes precedence over the hydroxyl group at the end of the branch containing carbon 4. This gives the branch containing carbon 4 the next highest priority, with hydrogen on the dashed bond as the lowest priority. Tracing the priorities gives an S configuration. However, because the lowest priority group is on a wedge, we flip the configuration to R. Finally, for carbon 4, the hydroxyl group directly bonded to it has the highest priority, followed by the branch containing carbon 3 for similar reasons as before, then the branch containing carbon 5, with hydrogen as the lowest priority. Tracing the priorities gives us an R configuration for carbon 4. D-ribose has three stereogenic elements, and because it is not a meso compound, it can exist as 8 stereoisomers. Let's move on to the next question. In biochemistry, amino acids are commonly referred to as D or L rather than using the RS system as homage to Emil Fischer's classification of sugars. All naturally occurring amino acids in proteins are L amino acids. Given below is a table of the 20 proteinogenic amino acids. Most L amino acids have their alpha carbon in the S configuration, but there are two exceptions. Which two proteinogenic amino acids do not have the S configuration? Feel free to pause the video and try this problem on your own first. The two proteinogenic amino acids that do not have the S configuration are glycine and cysteine. Glycine's side chain is a hydrogen atom, so its alpha carbon is bonded to two hydrogens, making it achiral with no chiral center to assign R or S. Cysteine, on the other hand, is chiral. The nitrogen in the amino group has the highest priority, and the carbon bonded to the thiol group takes second priority because sulfur has a higher atomic number than oxygen. Tracing the priorities confirms the R configuration, making cysteine the only other L amino acid without the S configuration. As always, thank you for watching, and I'll see you next time.